Hi, so another subject in Unit 1 is the stars and the celestial heavens. I have Weather Underground star charts program on my Android so that if I'm out at night, I can look up in the air, up in the sky, if it's a clear night, especially if I get away from the city lights, and look for constellations and planets. Also, my wife bought me this little book called The Night Sky when I was taking astronomy myself, and I like it because it separates all the different constellations individually and seasonally, and it has a little uh, itty-bitty flashlight to use so you can look at it at night. But it separates all the constellations and planets seasonally. But um, I can also look at the night sky with this star chart, or these star charts, and this is what I can find on my Android. I can change the part of the sky I'm looking at. I can go north or up or south, east or west. There's Mercury. And I can change the time. July 8th. Gee, that's today. Time 6 p.m. Well, of course, I can't see this at 6 p.m. because there's light out. It's not dark. So if I want to see, let's say I want to go tonight at 10 p.m. Okay. And then I hit change. Do the same thing on my Android. And now I can look at all of these different constellations that are all through the night sky. They're labeled, and you can do this on your computer like I'm doing or on your Android. One of the things you have to learn to do is lay down flat on your back and look at the sky, because if you're standing up, this part of the sky is behind you. It's over your head and behind you. This is the part you'll see if you're standing up. So it takes a while to get used to this. Also, you can click on, okay, planets is clicked on. So if there were any planets in here showing, I don't see any. I just see constellations. Constellation borders, redraw chart. There you go. So it's drawing borders around these constellations that might help you to find them easier. Constellation names are there. Planets are there. Star names. Let's put star names in. Individual stars here now. Deneb, there's Deneb. It's a part of Cygnus, which is the dove, I believe. Leo is way over here. Let's look at something I'm a little more familiar with. Let's look at January, 10 p.m. Change. And I want to see if we can find any planets. There's Auriga. I know Auriga. Let's get rid of constellation borders. Get rid of star names. Let's see, planets we still want to find. Redraw a chart, get some of that clutter out of there. Cassiopeia is this one that looks like an M or a W if it's upside down, depending upon the angle you're looking at. There's Auriga, that's easy to see in this night sky, usually very strong. There's Orion. Okay, let's see what happens when we go to 4 a.m. the previous morning. See where stuff is. Well, there's Cygnus way down there. There's Cepheus here. Cassiopeia is way down here. So things change in the sky depending upon the night. Here's Orion way over here. I'm not seeing any planets. Let's go to March. Let's go to March. And let's go to 2 a.m. Okay. Oh, there's Jupiter. Way over here, Jupiter. Usually that's the easy one to see. Let's look at it at midnight. See where Jupiter is. Okay, let's go to the west. Go to the north. I lost it. Okay, well, you get the idea. You can find the names. You can find the... There we go. There's Jupiter over here. Jupiter is easy to see. It's hard to see on this chart, but when you look up in the sky, it's easy to see. Moves across the sky. Remember that as these stars move this way, the planets move this way. The planets move in the opposite direction from the stars, and that's how you can tell where they are. Now there's another thing we want to look at, and that is carbon dating. They talk about the history of the Earth, and one of the ways we get an idea of what happened a long time ago is by dating the carbon that's in material we find, fossils, things that have died. Because once something dies, the carbon-14, which is a small percentage of the carbon is normally carbon-12, but one of the isotopes is carbon-14, it degrades. And I think the half-life is over 5,000 years. So it takes a long, long time for carbon to totally degrade, but the proportion of the once living material that is made up of carbon-14 changes, and it gets cut in half it's over 5,000 years. So we have an exercise here that you can look at, and I'm going to just play it and see if we can get the sound to work well for you. So when you took this homework home and read this article, you saw that there were some questions at the bottom. And basically the questions that are most important are, what proportion of the carbon-14 present in Otzi's body when he died is still there today? Well, in the article, you saw that the proportion is 0.435, or 43.5% of the 100% that was there in the beginning. And then the question is, when did he die? Well, in order to figure that out, we'll look at a bigger graph. We would go to the graph and we would extrapolate 0.4. Well, there's 0.5, right? A half is 0.5. 0.4 is right about here. We'll go over is right about there, and then we would go down to about here. So maybe 8,000 years old. We would be guessing that that's how you would use this graph. Well, it just so happens that there's a way to calculate it. Let's go back to the graph a minute. This is a curvilinear function. It's a typical logarithmic rate of decline using a natural logarithm, which means that the rate depends upon what was there initially. And so the rate changes as the initial material decreases. But it turns out that there is a direct relationship, that is a straight line through here. If we look at the logs of the relationship between the amount of half-lives, or the proportion remaining, and the amount of time. And so it just turns out that we can solve for Otzi's age by looking at this formula. And this T, that means how old the sample is related to the log of the proportion remaining, how much remains compared to how much was there, divided by a constant, decay constant for carbon, that is 0.693, times the size of the half-life, which is 5730, right? Well, this equation uses a radioactive compound that has a half-life that's down to 35%, I'm sorry, 35%. Otzi is not at 35%, Otzi is at 43.5%. So let's do the calculations on another sheet of paper. So if we use the same equation and we substitute in 0.435 for the proportion of carbon-14 left in Otzi and multiply the data out, we find out that 6,883 years ago it was that Otzi died. And by the way, the technique is accurate to within about 10 years, because one of you asked that question earlier. Interesting, don't you think? And then another interesting fact is that carbon-14 dating doesn't work too well after 1950. Do you have any idea why? Okay, Otzi was a frozen corpse found, I'll just read it to you, it's in the biology textbook. In the fall of 1991, sticking out of the melting snow on the crest of a high pass near the mountainous border between Italy and Austria, 2 Austrian hikers found a corpse. Right away it was clear that the body was very old, frozen in an icy trench where he had sought shelter long ago, and only now was released as the ice melted. So Otzi was a corpse that of a man who was killed a long time ago. He had an arrow sticking in his back. We don't know if that's what killed him, but he's been the subject of a great deal of study and a beautiful example of how carbon-14 dating is used to bring us to the time when he actually died. And that was over 6,800 years ago. So a good application for carbon-14 dating and a good explanation for the uses of this in our studies of the Earth and the biotic sphere of the Earth.